that's maybe to prevent maybe afraid of powerful ethics right up in the middle row. They're trying to prevent us to hear the next talk, but with all this some very small delay. It's my pleasure to announce our second talk today of Corentin Bodard, who will speak about in the intermediate geodetic group for virtually nilpotent groups. Yes, from the University of Geneva.
So here I'm going to talk about mainly geodetic laws. So the setup is the following. We have G finitely generated group as usual. And then we fix also geodesic S by height. I'm going to take it symmetrical. So it's equal to the inverse. And from those two this data, we can define the usual word metric. So I'm going to denote by 2 bars and subscript S, which is the set. So for each element G in G, it gives you the length of the shortest words over S, which represents G. And then what's usual, what you that is to consider the usual growth function. So it's some function which I'm going to denote sigma, which just counts the number of elements in G, such that the length is equal to n. So that's classical. That's just the spherical glossaries. And so maybe people look at that and try to compute it or try to find some properties of it, depending on some other algebraic properties of the group. So in this talk, I'm going to do something a bit different because I'm going to look at the geodetic rows. So it's kind of related, but it's also quite different. So the definition. So first, what's a geodetic? So a geodesic is just a word, so an element in this monoid over S, such that the length of the word is exactly the length of the element it represents. So it's the minimal, it's a representative for this word. I write a bar on top, it's the element instead. It's a minimal length representative for this element. So, alternatively, you can also see that as the word is labeled some geodesics in the K graph of G with respect to S. So that's a geodetic. And then the growth function we look at, it is not this one, but some slightly different one, is the geodetic growth function. Is another function. So I'm going to denote it by a gamma, and then as subscript, I need both G and S. For each integer n, it's just count the number of words of length n, which are geodesics. So I count just the number of different geodesics starting from the identity of like K graph. We're going to look at this. So another way to think about this is you count elements, but instead of putting weight 1 to each element, you put as weight the number of geodesics that link this element to the identity. So in particular, what I just said, some small observation is that at the standard glossary, the growth function is a lower bound on the geodesic one, because each element has at least one geodesic. So when you count all of the geodesics, you count at least one for each element on the field. If there's any observations. So maybe some example of geodesics growth function for the group. So let's start with easy, something easy. So examples. What happens if you take G to be just the intrinsic cyclic group, and you take as geodesic type just the user one, but then the K graph is really simple, as you probably know. It's a line, and so it's 0 here. And so for each element G, there's exactly one geodesic that links it back to the identity. And so what you get is that the growth function is always equal to 2, except for n equals 0. So you just get 2 geodesics for each length. Okay, so that's one thing. Maybe some other example. So what's tricky with this function is that it's actually strongly dependent on S. So when you do standard growth, usually it's the same up to some equivalence relation. But here it really strongly depends. So for example, you take Z, direct product with cyclic over 2. I'm gonna say that this one is generated by A, and this one is generated by B. Then I take just A and C. Then the K graph is just a ladder. And what you can see is that actually the geodesic growth is a polynomial. Actually, it's linear. You can go here, you can pick, you have to go up once, but you can go up whenever you want here on the line. So here this thing is polynomial. Even linear. But now if I take something slightly different, I take another link set for the same group, which is going to be A, so still the generated for B. And I can take AT. And now the K graph is more like this. So like this. And now the growth exponential. So you can choose to go up or down, it doesn't really matter. Except, I mean, you just need to finish your correctly. So then you get this thing is exponential. It strongly depends. Actually, I could give an example which is even easier. If you take any infinite group and you take as a genetic set 2 copies of the same genetic set, then you can see that every time you're going to get exponentially many geodesics, because you can take any copies of each other. So it really strongly depends on the genetic set. So that's for lines, okay? Not really. I mean, there's quite a big topic, but maybe an interesting one. What happens if you don't take lines? So if you take G to be Z squared. Okay, there's something really interesting that happens. So it's actually an observation by Shapiro. So it's always so that's an argument by Shapiro, I think in 93. I think. So I'm going to try to explain it because I think the argument is confused. It's also coming back later. Okay, take any S, any length S. So go picture. So S is like a cloud of points. Try to make it symmetrical. It should not be just important. So S, something like this. Then what I do is I look at the convex hull of the drink set. And I take any phase, any facet of the convex hull, so for instance this one. In particular, on this facet, I have at least 2 points from the direct sets. It's the 2 vertices. So I have here A, which belongs to the direct set S, and B also to S. Something I can associate with this phase is linear form, which goes from R4 to R, such that h of X is smaller than 1 for everything here below, so for everything in the polygon, and you have equality exactly on the face. Equality if and only X belongs to the face. Like this. And so now what the observation is that for any word for any word value, the length the value of h at the elements represented by word W, it's at most the length of the word, because each letter just add 1. With equality for W, which are word over the subalphabet, which is A and B. Those one they give you 1 exactly. And so this observation is to prove that all those words here, all those words over A and B, the minimal length for those elements represents. So from this you get that you have at least that many geodesics, so you have at least exponentially many geodesics. Like you 2T and already for any line. So for this example, you always have exponential. So what are the main question we can ask for? So okay, we have some example where it depends. Sometimes it's polynomial, sometimes it's exponential. Some other where it's always exponential. So the 2 main questions we can ask is some kind of minor Gromov question. You try to characterize groups where you have a polynomial degree growth. Because it depends, you need to put the correct quantifier. So the question is not well. So, question 1 is so Gromov and Miller question and Gromov answer is characterize groups such that there exists some S that the corresponding geodesic growth series, the geodesic growth function is linear, so bounded above by some linear. So for the usual growth, it would be just virtually nilpotent. So in particular, any group that has validity, because singularity has to be virtually nilpotent. So the first question, and okay, they must be virtually nilpotent, but we also have seen that this way doesn't work. So there's something more to say. And the second question, so we have something which is, we have some case where it's exponential, some case where it's polynomial. It cannot be anything be like greater than exponential because you have at most as many geodesics as words, and you have exponentially many words. The second question is, can you have something in between? So can you, does there exist a group G and a group S such that the corresponding growth geodesic growth is infinity. So here again, if you want to find some And for that, you should look either in the virtually total case or in the intermediate case. So with all the bigger examples and all the stuff. So I have some partial answer for this one, but mainly I'm gonna address the second one. Actually, the answer is positive, and I have an example which is positive. I mean, which I try to state now. Is there any questions so far?
When you say polynomial, you mean bounded above? Like,
Yeah, so
so is it true that it's always a fixed polynomial? I mean,
no, that's actually a good question still.
it's okay. It's okay.
Yeah, and this one is I think more complicated because
Yeah.
it's finer. So it could be like n to the
N to the
n times analog or some non-integral or even oscillate between.
Oh, yeah.
So it could be, yeah, but here it's just bounded above by, or here it's only bounded above by something. Okay, so I'm gonna try to put in the group which I use for this one. So I'm gonna define actually three separate groups. So the groups elements for my example, which I mean the example I'm gonna use. The formally you want to think about them as equivalent classes of let's say piecewise C1 path in R4. So there will be path in R4. You need to quotient something. So the operation is just concatenation. So okay, you need to make them something like 0, 0. And then the operation is concatenation. So
Bonjour Martha.
so okay, just to explain this last part.
Je suis dans un exposé, mais
So if you
online.
have two paths like this,
Les
then
exposés online, c'est difficile à suivre. Et j'ai coupé mon microphone, j'espère. Mince.
yes. So the convention will be like this. So now I need to explain what's the equivalent relation, right? So now it's currently just a monoid. I need to quote it, and it will be a group. So I need to associate to every path three parameters, and then I will use them to define the equivalent relation. So starting from 0, 0. So my two parameters, the first one is very easy. It's something I'm going to denote by G hats. It's going to be a vector, and it's just the second endpoint of the path. So pretty easy. Yeah, so then I need to do something auxiliary. So I'm going to define some auxiliary function, which is like a distribution of winding number. So I have a path G, let's say it's like this. Okay. Like this. What I'm going to do is concatenate it with the straight segment back to the origin. Now I have a closed path. And so I can define for each point in the plane, I can define the winding number of this path, this path around the point. So the function I'm going to define is the winding number of G, or actually the closed version of it, around xy, a point in the plane. So of G around xy. just to be clear. So you should count positively if you go anti-clockwise and negatively if you go clockwise. So here it would be positive +1 here, -1 here, and 0 outside it. Yeah. Yeah, and now I can define my two other parameters. So the second parameter is the sign area. So you can just write it as an integral of the winding number. That's pretty clear, I think. So here you should count, I mean, just look at this area and then remove this area, you get a number. And finally, finally, the last parameter is basically the y coordinate of some kind of barycenter defined from this map of this distribution of winding numbers. So I'm gonna do I'm gonna call it d of j, and it's again some double integral. So y times the winding number and your integratable plane, and so yd because it's like it's the y coordinates of some kind of barycenter function. So barycenter because you should divide by some area, but most here the area could be 0 to 3 almost divide. But anyway, real number. And so now, using those two parameters, we can define 3 groups. The first one is you take the implied of the path and you quotient by just the set of all paths where the endpoint is 0, 0. And the group you get is alpha. That's all you remember. So that's the first example. The second one is and then quotient by first the endpoint is 0, 0, and also the area here. And is well known. The number group with coefficient R. So is that the group of matrices with one diagonal, 3 by 2 matrices, one on the diagonal, any coefficient, any real coefficient over, and then 0. And finally, yeah, the third example, you do this, but then you quotient by the endpoint 0, 0, and R, and also this parameter should also be there. And what you get is some group, which is often called the angle group or some filiform nilpotent group. So it's 3-stat nilpotent. Yes, the smallest one, which is not 2-stat nilpotent. Okay, so all those are like continuous group, nilpotent groups, really not finitely related. So I need to define something which is finitely related, and then maybe you can talk a bit more. Anyway, even for those two groups, I think the definition with like the path is already like, you know, so to get 5-minute group, what I do is just I take some addition like that. So I'm gonna take some group which is 5-minute, which is generated by 2 elements A and B. And those 2 elements A and B is the path which goes the trajectory segment from 0, 0 to 1, 1. That's A. And then the trajectory segment from 0, 0 to 1, 1. That's B. And that's B which is generated by definition. So really that's what this thing is the group of on this execute grid. So yeah, 0, 0 here. So you have last pass on in this grid, and then you take the same equation. So that's nice. So if you do that in here, you get this graph. The discrete isomer group. So the same thing but with question in Z. And here you get some other group which doesn't have them. I mean, okay.
Can you please repeat it? You say you do it here or here. So what is your technical concept?
Sorry?
You just mentioned if you do this construction,
So it is well defined, but so you can put the limited and then quotient by different things and get different groups.
You repeat what D hat is.
D hat is just gonna path. So
You want all the paths that in there.
yeah, so if you do that, the only thing you remember at the end is the endpoint.
Yes.
And then when you go at it, it's just the endpoint. So you get in and so here, so two paths are equivalent to the same endpoint and the same area. So that's although you remember the endpoint and the area. And yeah, take the
the
same.
groups are step 2 important.
So this one is preset.
You say the portion the second commutator on you have some really.
So one set is important, this one is important, this one is 3 is important. Okay, maybe I should give you an element which is not here but 0 here. So I mean, okay, this 0 is a commutator, and then if you take the commutator with some other thing. So you do the loop, then go up, you loop in the other direction, you do the thing back down. Here you get something with positive area, negative area, so the total area is 0. So if I take the commutator of just a loop with not anything, I get 0 here, but now I get just some huge area down. So it's not 0 here. So yeah. And so that generates actually the center and the last layer in E. Okay, so that's okay, another group. And finally, what I need to I just add some last thing. So there's an automorphism about the 2, which acts on the 3, on the grid, which is just flipped by the y-axis. And so finally, the 3 groups you consider are this squared similarity with C2. So the similarity product of this subgroup with this morphic. So that's if you go solve by the first thing. The second one you get this group. And the last one you get nice 3 groups. This one is virtually abelian, virtually 2-stat impotent, which is 3-stat impotent. What am I talking about those groups? Because, well, This one, if you take a specific geometric set, S, which is going to be just A and T. So you don't need the B because, okay, maybe I should have said this. If you conjugate A by T, you get B. So conjugating A, I get this thing, and this thing will get here. So this is a geometric set for this group, and then for this thing you get polynomial this gross. So this is the results by Brighton, Burillo, Elder, and Zoran. In the paper, they provide a lot more of they all virtually abelian.
Only for the generated set or?
So no, there is much more.
But it's not known what happens in general for this group for all generated set or it's not?
Okay. So in their paper, they provide other sets and some sufficient condition, and I'm going to state right afterwards like the exact condition to get.
I didn't say even on this first management group, you will construct your examples with intermediate geodesic group or not?
So you need different ones.
Yes, and my question was about the first one.
Yes.
Yes, over this first one. Is group not intermediate?
Yes. So that's written by Alex Bishop. If you have virtually abelian, then you.
Okay, your second one is step, I don't see, it's step 2 or step 3, sir.
So it's virtually 2 steps, the second one.
Yes.
The last one is virtually 3
Yes.
steps.
And your main example is the last one, or?
Yeah.
And for the second one, what is this?
That's that will always be either polynomial or.
It's your result or?
It's a new result. Yeah.
It's your result.
Yeah.
Yes, I see. So your result in the second case also like in the virtually abelian, in the previous virtually abelian example of Bishop, you also have other polynomial for financial, right? And very interesting with your last example, right? You have.
So I extend the result of Bishop to virtual 2 step, and then
Yes.
for virtual 3 step, it's breakdown for good reason.
When you stay virtually to step for this particular one or for all virtual.
Sorry.
You say you extend the result of Bishop for virtually 2 step.
Yeah, for any 2 step.
For all 2 step or virtually 2 step important, you extend the result. Yes, and for step 3.
Yeah. Okay, so for why the thought that the only example where you have polynomial geodesic were virtually abelian, then yeah, I should look at the time. Actually, I don't know when I saw it.
I think you're about 30 minutes in. 30 minutes in.
So-
You're at 25. Yeah, you're 30 minutes.
This one is also polynomial growth. The result again by Bishop, which is Alex Bishop, and Marie Elder, which is in common, which is the previous one. And then this one is the interesting one. So let's just state it as a term.
There, it's polynomial for
This, yeah. Yeah. So the main theorem is the following. If you take this group here, and you take the same sets A and T, then you get that the growth is asymptotic to this thing, exponential of n to the 3, and there's a log which is this. So okay, this is just for a single example. It's a bit more general, but I'll just do it. So indeed, you get something intermediate. This is sublinear for at least one group. This one is virtually 3 steps. And so now I'm going to try to quickly explain both the upper and lower bound for the number of geodesics. So first, the lower bound. I think the lower bound is something which is much more general and which answers your previous question. So let's try to scale it as general as possible. So let's take G, which is virtually aspect important. In particular, we can find some subgroup finite index H, which is that's by definition. You can make it a bit better, you can take it normal, and you can take it so we find some subgroup like this, and then I need some more data to state the results. So I'm going to divide by pi the navigation map from H to navigation. Like this, because H really this thing is just and then yeah. So I need to define some polytope and some subset of it, and then this will give me the exact condition to get the code regime for the geodesic growth. So let's suppose G is limited by S. So I'm going to consider the trigraph of H in G, which with linking to S. Linking to the S, so vertices or cotet, right cotet, and then you have some edge from AG to AGX labeled by S. Everything is oriented and labeled. And so from this, I define some set that we call A, which is it's going to be a subset inside D. So I take Q a word over S, which labels a simple cycle from deposit H to itself. So, and then what I do is I evaluate it and I look at so this is as an in the subgroup H, and I look at in the evaluation, and then I divide by the length of the define some subsets inside RB. And finally, I define some polytope, which is the capital of A, and then I conjugate by GH. So G acts on H by automatic conjugation. And so of this thing on ZD, it makes sense hopefully. So okay, this quotient acts on ZD, and so then you can also make it act on A, and you get some. So just an example. In the previous, this is using an example. in this, I mean, any of those three groups are actually the same thing. And you take this shaping set, then the Schwer graph, which looks like you have loops. We have this. The picture and then that's by Schwer graph. And then what is A? I have three simple cycles from H to H. This loop A, this loop A inverse, and then this loop of length 2 divided by T squared. So in RV, I get A, which is those two points. So A inverse and divided by 2. And then the action again is just flip. So when acting, I get those 2 points additional, and then I can take the convex hull. And the theorem is the following, and I gone, so you won't get the answer exactly. Okay. The theorem is if A contains two elements on the same on a common facet of E, then the growth is neutral. This is really the argument by Shapiro. That means that you have two things, say here and here, on the same facet. And so, and you can, I mean, you have two loops here on the same point, and you can use them and fire any direction and go as fast as possible in the direction, and you get exponentially many geodesics. So that's the same argument as Shapiro, but otherwise, you get that this thing is bounded by exponential of C n to some power, and then you log with alpha s, which is a real between 0 and 1, which only depends on the step. And so you get that for alpha 1 and alpha 2, it's 0. And for alpha 3, you get and the rest is larger, but still smaller. So this means that in particular, for when you're in step 1 or 2, here what you get is really a polynomial. So in step 1 or 2, you get exactly exponential or polynomial. It's bounded by a polynomial. And okay, in the 3 step, for instance, you get this upper bound.
This because of S is increasing.
Yeah. And it's definitely explicitly, but it's not that. Nah, I don't remember it. Yeah. Anyway, I remember the third term because it's important. Okay, so that's for the upper bound. I don't know how to explain this thing fast. On the back of so now I'm going to try to explain really quickly the upper bound for this example specifically. So it doesn't work for any other example. I mean, actually it does, but I'm not claiming that it does. So here, I mean, the idea is really simple. You just need to provide the geodesics for any given length n to get the lower bound. So I'm just gonna give you a them quickly because I can't minute. So okay, you fix some n, and you want to have a lot of geodesics of length of the n. And so the geodesic I'm gonna give you the on this shape. So there's this shape, so some block of A1, right? Then you have T, T again, and then alternate. Okay, so I fix N. Also, I fix a K, which is going to be roughly epsilon, a small constant, and N to the restrictive, same constant. And so this thing goes on until I have A and K minus 1 plus K. And then what are the MI? So the sum of the MI should be N, and all the MI should be basically equal to the average. So that's the correct thing. This should be kind of close to the average, but we have some room at pH anyway. So that's the shape. I try to make it more visual just now, but just so that you see, like, here you have an epsilon choice basically, and you can make independent choice for K to get like the pipeline. Just hopefully you have some choice, some noise for each MI. What does it mean pictorially? So if you think in the group E, so with the pictures, what you do is here, you use A, the MI, so you go forward in one direction. Then T, what the T means is that instead of writing A's, actually you're doing B production mode. And so you get something like this. So I get B to the minus N1, so I get back here, and then minus N2, so I go to here. That's T. And I do this thing over and over. And I end up at this point and 0. So that's visually the geodesics. And I now want to prove that those are actually geodesics. So I'm going to look at the parameters and prove that if you take anything shorter, then it's not the same elements, and so those are geodesics. The two parameters I don't care about the area, but I care is the endpoint, N0, and the by. So the by, if you look at the winding number, here you have a negative winding number, so you start below and then you come back here. It's positive, negative, positive, negative. So you give negative above the axis and positive below the axis. So in particular, you get that y times the winding number is always negative. So the dy is really negative, it's like down in the with that. And so if you take anything shorter, well, you need at least that many A's that we have, because you need to go to this point. A is the only way to get to this point. So if you want something shorter, you will need to have less change in direction. But what happens is that if you have less rigid, then the triangle will be larger, and so you will get something larger in the one. So maybe just last word. If you want to have something which ends up here, and which has positive by or close to 0, there are only two solutions. The first one is to do as I was saying, change the size of the triangle. So if you have really small triangles like this, you get a by which is closer to 0, but it cuts the t's, so that's not the geodesics. And then the other solution is to add some big loop here to grab some positive amount of the area, but above the thing. But this costs 8, and so if you try to optimize, you see that actually those ones here, they're optimal. So those ones, they basically use this solution where you try to approximate as good as possible, but up to some point. So those are optimal if you try to. Yeah, if you do all the math and quantify everything, and so those are actually this. That's okay.
Are there any questions for the speaker?
So this is the only example where you do the exact things.
Well,
Or
okay, you can have. I can have other example with the same asymptotics.
yeah, I mean,
but I don't know,
for example, whether you can have like a slope to exponential, but still to
Yeah.
exponential, like that would be.
So that there you would need to, okay, either go in the intermediate case.
Yeah, because that's why I asked you, that's why I asked before if the alpha was increasing.
Yeah.
I mean, you should try push it to.
Yeah.
the
So,
exact CM.
Probably it is, but then when you want to get the matching lower bound,
Yeah,
you need
yeah,
to have
of
some intuition.
Yeah.
And okay, maybe the key thing here is that you can work, like usually people think you can work in 2-step.
Yeah,
Actually, I think you can also work in 3-step,
but
but I cannot work in 4-step or higher, so I cannot improve the level.
yeah.
Do you know of this group, there could be another finite generating set that gives something similar?
Yeah, so actually, I believe it. For this group, I believe there is something polynomial,
Yeah.
but it's not a symmetrical genetic set. For other 3-step, I believe you can go all the way to ends 1/2 here for 3 steps. But yeah, none of that is proven. And so, yeah, maybe there's a gap actually, which would be nice.
Yes, great. Okay, let's thank the speaker again. And I don't know, do you want to resume at 4:25 minutes to give
Yeah.
transition time and stuff?
Yeah.
Okay. Yeah, 5-minute break. Yes.
Yeah.